for this session will be what?
Your name.
Oh, okay. So I should introduce myself first. My name is Kevin Atienza and my handle is Kevin Sogo. Okay? So I think I'm most comfortable with math topics. So our session for today will be a somewhat math-heavy topic. It's about solving linear recurrences in faster than computing them manually. Okay? So along the way we will also touch on topics slightly related. For example, so you probably know what Fibonacci numbers are, and you maybe have heard of this formula. So this is the formula for the nth Fibonacci number, and as you know, Fibonacci numbers are integers, but this doesn't look like a formula that outputs an integer, right? But if you try it out with the various n, you'll notice that it indeed works. So even though there are square root of 5s here and there, after substituting various n's, they will indeed output the Fibonacci sequence. Okay, so our topic will be related to that, and also something about the expansion of this one. You probably know that this is the same as this expression here, at least for some bound, right? So this is just a geometric series, an infinite one, and then this is a closed form for that. Okay, so we will touch on those topics while we're trying to solve linear recurrences. So first, what is a linear recurrence? So a recurrence in general is something that, for example, a sequence defined in terms of itself. Okay? So for example, the famous Fibonacci numbers, we have the famous recurrence, which is each term is just the sum of the two previous terms. And there are other recurrences like factorial. So for example, n factorial is just n times n minus 1 factorial, okay? So when dealing with recurrences, usually we are given with the general recurrence, and then we have some base cases. So for example, for Fibonacci numbers, our base case is if the first one is 0, or the 0th one, and the 1th one is 1. So for factorial, we have 0 factorial is 1. Okay, and so on. So for any recurrence, we usually have the general form and then some base cases to start the recurrence with. Okay? And we can show by induction that the sequence is indeed well defined. So the trick with that proof usually is that you can order the arguments in some way so that you only compute terms based on other terms that were already defined. So for example, in this case, we start with 0 and 1, and then we compute the next terms one by one in increasing n, and the same with n. In some recurrences, the order is not necessarily the increasing order of natural numbers, but that's the idea. So we have a general form which is somewhat of a recipe how to compute the rest of the sequence, starting from the base cases. Okay? So the main problem is, for example, in the case of the Fibonacci number, given n, how do we compute f of n quickly? So this is a famous problem, and I'm sure a lot of you know the solution already. But one technicality here is that the Fibonacci number actually has a lot of digits. So if you compute the Fibonacci numbers, you'll find that the number of digits grows quickly. So let's say n is a million. There'll be I think, about 100,000 digits. So usually when you consider problems computing f of n for some large n, we usually take it modulo sum m. Okay, so in most of these discussions, we can implicitly assume that the computations will be mod some number m. Okay, so the problem is, given some huge n, how do you compute the nth Fibonacci number? Who here knows the answer? So, you, what's the answer?
So we will take the matrix 1 1 1 0 and then power n 0 1.
Yeah, this matrix and then take it to the power n. What happens when you do this?
Then that would be n plus 1 Fibonacci, n Fibonacci, n Fibonacci, n minus 1.
Okay. So this is one of the matrices that works. There are other matrices that works. For example,
0 1.
you do this, and there are reasons why they both work. Although the ordering will be a little different, but in any case, you will still get the Fibonacci numbers that you want. Okay, and why is this fast?
Log n.
Because you're using a power, and you can compute that using a fast power algorithm. Okay, you know there's an O of log n algorithm to compute the nth power of anything. You just repeatedly square if n is even, and then if n is odd, just multiply it once, and then it becomes even. So our goal is actually to compute linear recurrences, which is a generalization of the Fibonacci numbers. So a linear recurrence is something like this.
Fibonacci numbers can be calculated without matrix exponential also.
Yeah.
Like we can draw, imagine a line. So if we are at nth position, and if n is 2 into k, so we can either go from n to k and k to 0, or n to k plus 1 and k plus 1 to k minus 1 when there is 0.
Yeah. So in the case of Fibonacci numbers, there are more specialized algorithms. But in this session, we won't consider those. We will consider techniques that apply equally to all the other linear recurrences, not just the Fibonacci numbers. Okay? So I'm saying that a linear recurrence is something similar to the Fibonacci numbers, but the coefficients may not necessarily be 1, and the number of terms could be more than that. Okay? Something like this. It can go on for, let's say, k terms, some coefficient, and n minus k. Okay? So given this recurrence, and along with some base case values, let's say the first k terms, how do we compute f of n quickly? So, how many of you have encountered some similar problem to this? Okay, so we'll go quickly through this. There's a famous algorithm that works for this. The keyword for this is matrix exponentiation. So similar to the Fibonacci numbers, we can also set up a matrix that computes linear recurrences quickly by exponentiating some matrix. So how does this work? Let's say, for simplicity, we are dealing with order 4 recurrence. So let's say our sequence is f of n. So we have an order 4 recurrence, and we are given the initial 4 values, and our goal is to compute f of n. So what is the matrix that we have to exponentiate to get the values? Yes?
It's a 4 cross 4 matrix containing values. In the first row there will be A, B, C, D. Then it will be 1, 0, 0, 0.
Okay.
0, 1, 0, 0, 0, 0, 1, 0.
Okay.
And then we have to multiply with another matrix. F3, it is a 1 cross 4 matrix.
Okay.
4 cross 1 matrix, sorry. F3, F2, F1 and F0.
Okay.
So what we get is the next values like F4, this is equal to another 4 cross 1 matrix, which is F4, F3, F2, F1.
Yeah. So this one is pretty intuitive. So we set up a matrix that has a regular form like this. The coefficients are in the first row and a slightly offset diagonal of ones. So what this does is, if you try to multiply this vertical vector, you see that the next few rows just pushes it down. So F3, because of that, it will be here. F2 and F1. Okay, so this one will be removed. These three will be put here. And then this appears because if you multiply it by the coefficients, you get the next one. Okay? And if you multiply that matrix again, you get the next few values. Okay? So the idea is raise it to n and you will get this. Okay, so you get f of n along with other values. You can just ignore it. Okay? So how fast does this work?
So we can also compute this to the power n minus 3 instead of this. So it will be a bit.
That's just 3 multiplications. So this is, I think, when you do it like this, you get rid of some tricky cases. Let's say you want to compute f of 0. So if you want to compute f of 0, you'll raise it to n minus 3 or something. So you have an additional if in your statement. Whereas in this one, you just multiply and then get the term you want. Okay? It's a little thing because it's just a small thing because minus 3 is just a really small number. When you're exponentiation, it doesn't really matter. Okay? So what I'm asking is the time complexity of this.
K cube log n.
K cube log n.
It's k cubed log n because where k is the size of the recurrence because the matrix is k by k. And when multiplying two such matrices, you need k cubed time and you need log n multiplications. Okay? So
if there are 4 terms but the last term is f of n minus 10, you would have to create a 10 cross 10 matrix.
yes, so that's another trick with this. So don't be fooled by this regular form. Sometimes some terms disappear. But if that happens, you can just assume that the coefficient is 0. So let's say I say f of n is f of n minus 10 plus f of n minus 16. This is actually an order 16 recurrence. So you will have to build a 16 by 16 matrix. And a lot of the coefficients will be 0, but that's okay. Alright, so that's one trick. If the offsets are not consecutive, you can just fill in the missing values. Alright? So let's find some modifications, some other modifications because it looks like we have solved the linear recurrence, right? So what else does there need to be done? So let's try a small modification. It's still pretty popular, but it's a good starting point. Let's say our recurrence becomes so what should we do? How do we compute f of n quickly given these conditions? Yes?
Add plus 1 to both the sides,
Yeah?
and then we can substitute it with g of n.
You mean like this?
Yeah.
So, right, you just offset the recurrence by 1 and then it becomes the Fibonacci-like recurrence. So we can use our previous algorithms, right?
Maybe the matrix here
What?
will be the same.
Yeah, the matrix will be the same. Although you have to add 1 to the initial values, and then in the end you have to subtract 1. Or maybe it's the other way around. But the idea is just offset the coefficient or the whole sequence by 1 and compute the Fibonacci recurrence and then return by removing the offset. Okay? So, does anyone understand that? Does everyone understand that?
Can you give an example, like how will we do this?
Oh yeah. Okay. Let's say the recurrence is a little more complicated. This one. Random coefficients. How do we solve this?
We can add one more row at the end of the matrix for the 2.
Okay, so that's a little different approach. But do you think the offset approach can work still in this? Yes? So how?
You would have to find what number to add.
Okay, so what number to add? What do you mean what number to add? Just add to both sides?
You can add 8.
Yeah, a different approach is that you know that we're trying to offset the sequence. So let's say we define a new sequence like this, where it's offset by some constant c, and then substitute it back. So this becomes c. Okay, and then when we do this, we have something like this. Okay, so I move the c's on the right side, and we want these to cancel. So what should be the c here? So this is 9c equals minus 2. So we want c is minus 2, 9. Okay, so random coefficients, you get a random constant, of course. But it's true. If you offset by this constant, you get a recurrence that doesn't have this. It's a pure linear recurrence. And you can use the matrix approach. Okay? And this isn't restricted to order 2 recurrences. We can do this with any size recurrence. And one trick. This is a fraction, so how do you deal with this? I hope you know that you can take 9, the inverse of 9, modulo your modulus. Okay? But that's a small thing. So the general idea is to offset the whole sequence, so you can cancel out the constant. Do you think that can work all the time?
We can make changes to the matrix.
Yes, but I'm asking this approach first.
What if
Does this
modulo
does
divides?
what?
Modulo divides that number.
Let's assume that the coefficients are small enough, so it doesn't divide. Okay, of course, if that happens, then you have to use another approach. But can you think of a flaw in this approach? Do you think it will work in all kinds of linear recurrences with another constant?
No.
No?
Cancel.
Why? Oh, don't answer that. I want someone to think.
It cancels over.
What?
The coefficients of constant are equal.
Yes, it's possible that everything cancels out, the c, so you can never solve for c. An example is this one. So, if you try to find a constant c, then you'll get the equation 0 equals 3, which is absurd. So you cannot do the offset thing. Okay? Another is this. I hope you see the pattern. So these are binomial coefficients. And do you understand why it works when we do this? Actually, it's not only this. There's a reason why the offset thing doesn't work for certain linear recurrences. We can touch on that later. Okay? So the idea is that if the sum of the coefficients on the left side is equal to the sum of the coefficients on the right side, then of course the constant will cancel out. Okay? So you cannot use that offset trick all the time. But someone else mentioned an approach of modifying the matrix. So how does that work? So for example, in this case, what can we do? Yes?
You can take the first matrix as 2 minus 1 and 1, 2 minus 1, 1, and then 1, 0, 0, and then 0, 0, 1.
0, 0, 1, and then?
And then multiply with another matrix, it's F1, F0, and 3.
Okay. And you get F2,
F1 and 3.
3. So the idea is just stuff the constant down here, and you can use it anywhere. Actually, an even better approach is just do this. We made the constant 1 so that if you have other constants anywhere in your state, you can reuse the same cell instead of having multiple cells for different constants, right? You just change the coefficient.
How do we make that matrix?
Okay, so how did we make this matrix? So the idea is we want this. We want to find a matrix that transforms this into this. Okay? We want to find that matrix. So this one is easy. Just write this row here. And this one's easy, just do the offset thing. And then how do you compute f of n? Take the coefficients. And the 3 is here because it multiplies to 1. So we exactly get this. So we can prove by induction that this is true. Okay, everything here is powered by induction, by the way. So as long as you know the order in how to compute the terms of the sequence, then everything else follows by induction. Okay? So the idea is to stuff a 1 here so you can use a constant. This works even if we cannot use the offset rule. Okay? And this works even if the recurrence is of any size. So what happens is that you'll have a coefficient, the coefficient row here, you have an offset 1 here, but the 1 on the last row is on the last column as well. Okay, so there's a gap here because we want to copy the 1. Okay, so that's the main idea. So what about this? How do you solve this recurrence? Any ideas? Yeah?
We can add 2 more rows in our matrix.
Okay.
One is for like first thing is fn minus 1, then is fn minus 2, then is n, and then is 1, 1.
1. Okay, so what your goal is to find a matrix that transform this into
fn minus 1, n plus 1, 1.
okay. So I hope you're getting the pattern here. If you have a set of states that's always finite in size and the transition is linear and is always the same, then the matrix exponentiation thing will always work. Okay, so in this case, what's the matrix? What's the first row? Anyone?
This is minus 1. So how do we get n to n plus
3, 0. So you get 3n. Okay? What about this one? Just copy the one, push it down. The next one, 0, 0, 1, 1, because you want n plus 1, so we add this. Okay? And this one is copy the 1. Okay, so you see the idea, as long as you have some kind of thing that can be written as a linear recurrence as well, you can use the matrix approach. Okay? The more general form of this is, let's say we have 2 recurrences. Let's say we have we have this. Let's say we have two recurrences. Okay, so f and g are defined in terms of each other. Let's say we have four base cases, f0, f1, g0, and g1. So everything is well defined. How do you compute f of n quickly? So the idea is find a column matrix that can be transformed to a similar column matrix using a square matrix here. So what should be placed here and here, and what should be placed here?
Fn minus 1, Gn, Gn.
What?
Fn minus 1, Gn, Gn.
Fn minus 1,
Fn minus 1, Fn minus 2.
Gn minus 1,
Gn.
Gn minus
Okay, so we want it to transform it into.
1. Fn minus 1, Gn.
Okay, so I think the drill is clear here. So in the first row, you write the coefficients A, B, C, D. In this one, you'll write E, F, G, H. In this one, you want to copy F minus 1, F of n minus 1. So it's going to be like this. And it's going to be like this. Okay? So, and it can work with any number of mutual recurrences. Even if we add some plus 1s or plus n's here, or even plus n cube or something. Okay? You can write a large enough column that contains everything you need to transition to the next one. Okay, so for example, in the n cube one, you'll probably want to write all of this. And then you want to get this. And luckily there are ways to get this from this. Just expand this one. Okay, so you'll get some binomial coefficients here. Okay? So that's the main idea. And why does this work? Why does it work even if we add some polynomials here? Because polynomials are linear recurrences as well. Okay? So for example, we do this. Actually, we can also write f of n equals f of n minus 1 plus a. Okay, but a, you can we can write a sequence like this: cn minus 1 and cn is just a constant sequence. So there's no constant anymore. Everything is a coefficient of some linear term. So that's the reason why everything works, even if we add 3n plus 1 plus n cubed plus n to the 5. Because all of these polynomials can be written down as some recurrence. Okay? Actually, if you think about it, let's say you want to write n squared as a purely linear recurrence. You have this equality, n squared minus 2 n minus 1 squared plus n minus 2 squared equals 0. Okay? You also have n cubed minus 3 n minus 1 squared plus 3 n minus 1 cubed minus n minus 3 cubed. Okay? All of this can be verified algebraically, and the coefficients are binomial coefficients with alternating signs. Okay? Something like that. Maybe I'm wrong in some of these exponents or something. But all of this you can verify algebraically. Okay. Of course, if you have a higher degree here, the matrix will be larger, so the algorithm will be slower. But
So, what if k cube log n is greater than n cube?
if k cube log n is larger than n, then there's
Okay, nk.
nk. If that's larger, then don't do this. This is worse. Okay? You only do this if this is better than this, which happens when n is very large, k is not very large. Okay, so it depends on the constraints. This isn't required, and actually sometimes it's worse. Okay, I can easily set k and n to be equal, and this will be better than this one. Okay, so you have to look at the constraints, and you have to know the size of the matrix you created. Sometimes it's part of the problem to make the matrix as small as possible. In certain approaches, sometimes you get a large, let's say 100 by 100 matrix. But if you find clever insights, you might reduce it to say 20 by 20. And that's a huge improvement. Okay? But the general idea is the same. As long as you have everything you need and you have them as few as possible, you can find a matrix as long as everything is linear as well. Okay? So there's another modification of it. Let's say f of n is a f of n minus, let's say 2f of n minus 1 plus 3f of n minus 2 plus 5 raised to n.
This is not
Is it? Can you find f of n quickly if the recurrence is this?
Yes, we want to transform fn minus 1, fn minus 2, 5 to the power n minus 1.
Yes. Something like this. And you want to transform it to fn minus 1, 5 of n plus 1, and 1. And how do you do that? Yeah, just multiply this by 5. Okay? So this 5 to the n, it doesn't look linear. Yes, but it can be defined with a linear recurrence. So you have some sequence that each term is just 5 times the previous one. Okay, so that's the reason. Yeah?
Can you please tell me the reason why you are taking up 1 there? What the significance of 1?
Oh no, the 1 is not required. So that's part of the problem. So sometimes I just place everything that I could possibly need, and then later on I can remove things that I don't need. Okay, so in this case you're right. 1 is not needed. Okay, but if I add 1 here, it's now needed. Okay? So do you get the idea? What about if I place 5 and 9 times n here?
We store both n and 5 to the power n into n.
What?
We store both 5 to the power n into n and n.
And what?
5 to the power n into n and also n.
N to n?
I think 5 to the power n into n.
Multiplied by
5 power n into n.
Can you just write it? N. Okay, so how do you make the transition? So I presume you want this to be like this, right? And this one to be n plus 1? Okay, so how do you...
We could also require 1 for this.
What?
Additional 1.
An additional 1?
This is it.
Okay. So what's the matrix? Can you do this? Can you transform this into this using a matrix? So this one is fine. Okay. This one is fine. The only thing remaining is this. How do we get this from everything?
0, 0, 5, 5, 0.
What? 0, 0,
5,
0. Is that right? It will become 5 to the n plus 1 times n plus 5n. That's not right.
5 to the end.
What?
We should also
We don't require n as well. We just require 5 to the power n.
Yes. We have to add 5 raised to n. Okay? That's the idea.
Yeah, so just get rid of the 5 over there, and
Get what? Get rid of what?
so we change our row to 0, 0, 5, 0, 0, 5.
Okay, so what you're saying is we want this. And that's right. It's equal to that. Okay, so you need 5 raised to n as well. And actually, you don't need these terms. You only need these terms. Okay?
So while writing these matrices, how can we efficiently, quickly determine that what we need? That is, it's not quite able to write everything possible, n, 1 and 10.
Okay, so the general idea is, we'll get to that, but let me give out one more example. Let's say one this will be n cubed. Do you think you can still do it? You can still find the matrix?
N square n and 1 also. No, not 1 n square and n.
5 n square.
So what? What do I write?
5 to the power n into n cube n square n.
This? Do you agree?
We
No.
need 5 to the power n square. We don't need these 5 to the power n square, 5 to the power n and 5 to the power.
Yeah, this is the correct one. You don't need the polynomial terms. Okay, you have to stuff in 5 to the n every time. And it's going to be similar to the polynomial one, except there are 5s everywhere. And if you really derive it, I'm sure you can, if you expand everything, you'll get terms like this, right? And the coefficients will be constant, okay? In your example, you wanted n cubed, n squared, n and 1. Unfortunately, there's the 5 raised to n here. You can't multiply by 5 raised to n because you want the matrix to be constant. Okay? So the main idea is, let's say you want, if you add something here that's the form a raised to n, n raised to b. So what are the terms that you need to add in the column?
A raised to n, n raised to power b, a raised to power n, n raised to power b minus 1, a raised to power n, n minus b.
Yeah. All the way up down to a raised to n. Okay, so the idea is really the same. Okay? So that's the main idea. And terms like this, there's a reason why these can be written down as a linear recurrence. Okay? We'll get to that later. So now at least you have some familiarity of the technique of matrix exponentiation. As long as you have some kind of recurrence, probably from some dynamic programming problem, and the states that you need are finite, and the transition is always the same, and they're all linear, then you can probably use the matrix exponentiation technique. Okay? So in our particular problem,
So,
yeah.
so is there a way to do this matrix exponentiation technique without using the matrix, like you can use Fibonacci?
It's gonna be hard. I'll describe a few techniques that we can do, but they're not always a better solution. Okay? So right now our solution runs in of k cubed log n, where k is the size of the matrix. Okay? So if we're computing a recurrence of size k, then the matrix will be k by k. Okay, so the next part of our session will be tackling how to compute this further, faster. Do you know how to do it? Okay. So, any ideas how to do this faster than k cubed log? Yeah?
You can use Cayley Hamilton theorem.
The what?
Cayley Hamilton theorem.
The what?
He's saying Cayley Hamilton theorem.
Oh, Cayley Hamilton theorem. Okay, that's good. But I won't tackle that because I want to go to a different technique. Okay? So the Cayley Hamilton theorem is a statement about a matrix, its characteristic polynomial, and a thing that is satisfied by the matrix. I mean, the matrix also satisfies its characteristic polynomial, something like that. And using that, you can compute the matrix power, I think, quicker than this. Okay? But I'm just asking some for quicker ways. So a cheap way of doing that is just to use a fast matrix multiplication algorithm.
Is there a faster way than k cube?
Yeah. I think the name was Strassen's algorithm. and that runs in k log 7 base 2, right? So it's a cheap way, but it's probably not going to give you any speed up because this has a large constant. There are other faster matrix multiplication techniques. I think you can get the exponent down to 2 point something, 2.3 or something.
2.36.
2.36. Okay, that's the state of the art matrix multiplication that we have. Okay? I don't even know how it works. But do you think we can do even better than that? Okay? This is the most common one. I think a lot of people know the matrix exponentiation technique. But not very many people know that it can be improved further. In many cases, I don't think it's in all cases you can do this, but in many cases, in particular in linear recurrences, you can improve this running time, and the code is not really that hard to implement. Okay? The idea is we need to use generating functions to find the solution. Okay? This is a technique. I don't know if there's a better way to expose this technique, but this is how I invented it, and this is how I understand it. So this is how I'm going to explain it. Okay? I think it's pretty intuitive anyway. So let's say we have a linear recurrence. Okay, so the general form is something like this. The coefficients are the A1s, the AIs. So something like this.
So the examples you dealt here, like the one that fn equal 2 fn minus 1, that isn't linear recurrence, but
Yeah.
still we can use that matrix technique.
Yes.
Yeah, so that is where, that is what would be the more general statement that if this satisfies, then we can use the matrix exponential.
Yeah. So the idea is, in our previous examples, these are not purely a single linear recurrence, but you can easily prove as well that if you can find a matrix, something like this, we have a lot of things in here, then you can find an order k linear recurrence for
Yeah,
any
but I
term
am
in
asking
this.
some more formal kind of like
What?
more formal stuff that you are telling that if we can put that thing in a column and then find suitable values so that we get that recurrence as mentioned, then we are done.
Yeah, but that's k cubed. We want to
Yeah.
improve.
No, I am asking about that only, that how are you actually telling that when can it be added? Is there any some formula that if this recurrence can't be solved using the
The keyword here is linear. Okay? By linear, I mean, so you have a term here, and then there you have a sum of terms here, each of which is a previous value in the sequence. Let's say this one, or maybe some other sequence that is also linear, and the coefficients are constants. And that's it. If you can write it in such a form, then you can make a matrix. Okay? And you have to ensure as well that this holds for all n. The size is not infinite. I mean the terms here are of a fixed size. Okay? And that size determines the size of your matrix. Okay? So that's the idea. But we want to improve. So this is the general form. How do you think can we compute f of n quicker than k 2.36 log n? Okay? So for this we have to digress a little bit and discuss generating functions. Now, generating functions in general are a highly useful tool in, for example, counting problems and finding closed forms to certain recurrences. In this case, we will be using generating functions to possibly find closed forms for linear recurrences. Okay?
What are generating functions?
Yeah, I'll discuss it. So the generating function, you can think of it as a function, just a function. Okay, let's say f of x. So let's say this one is a function. So why is it called a generating function? Remember what we talked about earlier? If if you expand this, it generates some sequence, right? Specifically, the coefficients are all ones. So we say that this function generates the sequence of all ones. Okay? And a lot of functions do this. Also, of course, we have to add across something like this. But later on, I'll describe that you can ignore the compounder conditions. Okay? Of course, you can try it for other functions as well. If you try it with 1 minus x squared, you get something like 1 plus 2x plus 3x squared plus 4x cubed plus dot dot dot. So this function generates 1, 2, 3, 4, 5. Okay? Of course, we can also write 1 minus 5x, and that generates 1 plus 5x plus 5 squared x squared plus 5 cubed x cubed plus dot dot dot. So it generates the powers of 5. So in general, something like that. And in fact, our goal is to find a generating function for our recurrence. Okay? Let's start with the Fibonacci numbers. So the Fibonacci numbers are defined this way and this. We want to find a function such that it is equal to this. So it expands to this infinite polynomial or series and the coefficients of the Fibonacci numbers. So what do you think should the function be? That's the goal of this discussion. Okay, and along the way, what does it mean anyway when we say that this expands to this? And how about the condition x is less than equal to, is less than 1? The absolute value of x is 1, less than 1. So all of this sounds like calculus or something, right? But actually, we can ignore all of those calculus considerations by just considering this as a purely algebraic object, which we can multiply. Remember that during algebra, you multiply polynomials sometimes, but behind the scenes, you know that those polynomials are actually formulas, where you can plug in some x and then you get some number, right? So when we say that x squared minus y squared equals x minus y, x plus y, we're actually saying that this equality holds true for every x and y that we substitute to this equation. So that's what we mean when we add, multiply, or compare polynomials, right? But in this case, we can actually treat them as an object themselves. We can consider x not as a placeholder for a number, but just an object in itself that you can add to other objects, multiply, subtract. Okay? For now, just forget about x being a real number or anything. X is just an object, and you know how to manipulate that object. For example, you know how to do this operation. This is just x raised to 5. Okay? But x is not a real number here. X is just an object that satisfies this law. Okay? That satisfies this law. And some other things that are very intuitively algebra stuff. Okay? So now, what do we mean when we say that this is equal to this? If we rewrite this as this one, and then if you try to expand this as a purely algebraic object, not caring about this condition whatsoever because x is not a real number, what do you get? So you get 1 minus x plus x, so it cancels out. Minus x squared plus x squared, so it cancels out. In fact, everything else cancels out except 1. So that's what we mean when we say this is this. Okay, we're saying that the inverse of this expression is this expression. And x is not a number here. Okay? So at least that's clear. And we're also saying that 1 minus x squared is 1 plus 2x plus 3x squared plus 4x cubed plus dot dot dot. What we're really saying is that if you get this expression multiplied with 1 minus x twice, then you'll get 1. And you'll in fact see that everything cancels out. Okay? And we don't care about which domain x converges because there's no such thing as convergence in this world. Because x is not a number anymore. Okay? And that's what we mean by generating functions. This is a generating function. It's a function, although it's a little misleading because there's no input and output, there's no domain and range. There's just x and then the expression. Okay? We call it generating function anyway. And the nice thing about generating functions is that they satisfy some algebraic properties. If you take objects like this, then you can add them, you can multiply them, you can subtract them, and they satisfy the laws that you expect them to satisfy. For example, commutativity, distributivity, associativity, and in fact, we also have an additive identity. If you consider the zero expression, or just the expression with everything zero, this is an additive identity. This expression is a multiplicative identity. By the way, when we say 1 minus x, what we really mean is 1 minus x plus 0x squared plus 0x cubed. So in fact, everything that we write here is just an abbreviation of some infinite series. Okay? So if you just take all the generating functions, then they form some kind of good structure that satisfies all the algebraic laws that you want them to satisfy. Okay, the technical term for this is that they form a ring. Okay, in fact, a commutative ring with unity. Actually, I think they also satisfy a property called they don't have elements that are called zero divisors. What I mean is that you cannot find two generating functions such that when you multiply them, they become zero. But originally they weren't zero. Okay? So what does that mean? So if you find this equality, then you get A equals 0 or B equals 0. Okay? So that's another nice property. Okay? We use this all the time when we're solving things like this. We factor it out and then use this property. Okay? It turns out that generating functions have that property as well. So in general, if you look at generating functions as objects on their own, they're actually they form a very interesting structure. And in fact, they will help us solve this. Okay? So what do we do? How does this relate to generating functions? Consider this. So I was talking earlier about finding this formula, right? Where f is the Fibonacci sequence. Imagine that you multiply it with this generating function. What happens? This is kind of magical, but I'll explain later where it comes from. But let's say we pick some random sequence here. Okay, let's say this is 3. And let's say we multiply this by minus x squared, this by minus x, and this by 1. What happens? What's the coefficient? This one becomes minus f1 x cubed minus f2 x cubed plus f3 x cubed. Right? And note that because f is the Fibonacci recurrence, everything cancels out. Okay? So in fact, if you take this and multiply it by almost all terms, almost everything cancels out, except possibly the first few terms. So what you'll find, if you substitute the initial conditions we have, you'll find that this expression is equal to x, just x. Okay, so we have the equality x equals 1 minus x squared, the Fibonacci series. So we can divide by this. And now we have a generating function for the Fibonacci recurrence. But how does that help us? So we want to find Fibonacci numbers quickly, but all we got is some generating function. The trick here is that you can write something like this into something like this. This is called partial fraction decomposition. The idea is that if you combine this, you want to select B and D such that they multiply exactly to this. And then you want to select A and C so that the top one becomes exactly X. So in this case, what numbers do we choose? So if we expand everything, we get A minus ADX plus C minus BCX over 1 minus, let's try to multiply the denominator, B plus D X plus BD X squared. Okay? So we want this to be the same as this. It means that B plus D must equal 1 and BD must equal minus 1. So you have this, you can easily solve this. This is you can solve this using the quadratic formula. So essentially we're finding the roots of some polynomial here. Okay, and in fact we can find that here's one possible set of solutions. That's why you see all those squares of 5s there. Because that's just the roots, the inverse of the roots of this formula. Okay? And then after you get D and D, you want to select A and C so that the top one becomes X. So what we get is, I think we get A is equal to 1 over square root of 5 and C equals minus 1 over square root of 5. Okay? So we can write X over 1 minus X squared as 1 over square root of 5 times 1 over 1 minus 1 plus square root of 5 over 2x minus 1 over square root of 5 times 1 over 1 minus 1 minus square root of 5 over 2x. Okay? The numbers are not so nice, but the idea is just you want to decompose this into this. Okay? Once you get that, notice that this term is quite familiar. This is just this term. Okay? So you know that this expands to, this term in particular expands to 1 plus 1 plus square root of 5 over 2x plus 1 plus square root of 5 over 2 squared x squared plus 1 plus square root of 5 over 2 cube x cubed and so on. Right? We just substituted something here. And the same with this. So in fact, we can add those two things and we get the famous formula for Fibonacci numbers. Okay? So this formula that looks kind of magical is actually just a product of the theory of generating functions. Okay? And in fact, if you have another recurrence, you can pretty much do the same technique. You'll get some closed form formula for it. Although sometimes you'll run into trouble. In this case, we were lucky that B and D were distinct, but sometimes B and D are not distinct. And if the polynomial here is has a large degree, you can have multiple repeated roots, etc., and all sorts of complications. But it turns out that everything else has a nice form. So let's say we have something like this. Okay? So this actually expands to, I think, something like A 1 minus x plus B 1 minus x squared. Although we have to find A and B. Let's say this is if we select A and B properly, we will get something that's equal to that. Unfortunately, this term is not like that. Okay, there's a square. But as you remember, 1 minus x squared can expand to this. Okay? So, in fact, you can still find this closed form formula for this. So, 1 minus x squared in particular generates this. So that's why we get the polynomial ones. Remember that we were doing matrices n1. That's why we can do this because of this thing. Okay? If you do this, then you get some sequence here that grows quadratically. That's why we can do this on our matrix approach. Okay? And then if the root is not 1, let's say this one is 1 minus 4x plus 4x squared. This will become 1 minus 2x and 1 minus 2x squared. Again, there's a square here, but we know how to expand that. So actually this one expands to 1 plus 2 times 2x plus 3 times 2 squared x squared plus 4 times 2 cubed x cubed, etc. So what we see is actually we get the term n plus 1 2 raised to n. Okay? That's why our approach earlier with n times 5 to the n, that's why we can write this as a linear recurrence as well. Because of things like this repeated roots. Okay? So in this case, the root 2 is repeated. That's why there's an n plus 1 here. If the root 2 is repeated even more times, then you'll get a larger polynomial. Okay? So that's the main idea. Using generating functions, you can find closed form formulas for your recurrences. Yes?
Why is this method useful? Like, if you want to, like, it will reduce the complexity from k cube log n to k log n, right? Because, like, you have k roots in general.
Yes, I think.
So my point is that we would want this to happen only if k is sufficiently large, like 100 or something.
Yeah. So this is not the solution I'm talking about. This is just an explanation on why we can do the matrix thing. Because this is kind of magical. You get an n cube, and you somehow can get n plus 1 cube using some coefficients. This is just an explanation on why that works. Those terms are actually linear recurrences as well. Okay? So now, we want to find the fast solution. So what do we want to take away from this process? If we have, remember the Fibonacci numbers, we get this generating function. If you do exactly the same thing for a more general recurrence, you will get something similar, something like this. Some polynomial over some polynomial. Okay? So, and this polynomial has a smaller degree than this one. And furthermore, q of x actually reflects the coefficients of this recurrence. Okay? So, q of x actually looks like this. 1 minus a1x minus a2x squared minus a3x cubed minus dot 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 until akxk. Okay? So in the case of Fibonacci numbers, you see that these are the coefficients 1, 1 in the Fibonacci recurrence. But if you have a more general recurrence, the denominator will look something like this. Okay? And the generating function of any linear recurrence will look something like this. Polynomial over polynomial. Qx is this, and p of x has a smaller degree than q of x. Okay? So, what do we want to take away from this? So, any linear recurrence has this generating function. Conversely, any generating function of this form determines some linear recurrence. Okay? So what? So for example, we take x plus 1 over 1 minus 2x plus 7x cubed minus 7x9. This is kind of a random polynomial, but right away I know that this generates a sequence with the following recurrence. Because, as we said before, q of the denominator has the coefficients. Okay? So try expanding this using some math techniques. You'll find that the coefficients satisfy this recurrence. Okay? This one as well. So now you get the idea. So how do we optimize? So how do we use this, exploit this to find a faster solution? So the idea is to use this equality. If R is some non-zero generating function, then this holds trivially, right? Okay? But we can exploit this by choosing R in a very particular way so that we can essentially ignore half the sequence. So how do we do this? So the idea is, one first requirement we want is that R has the same degree as Q. So what does that make? What happens when we multiply such a polynomial here? Then, suppose the degree of Q is K, then the degree, what will become the degree of the denominator here? 2K, right? Because they have the same degree. So when you return back to the recurrence, you'll get an order 2K recurrence. So it becomes larger. But our goal here is to select R such that only the even offsets will have non-zero coefficients. So we can essentially ignore the odd offsets. Can we do that? Our goal essentially is to find a polynomial such that if you multiply it with Q, you get the polynomial f of n is equal to 3fn minus 2 minus f of n minus 4. So you can check, in fact, that the Fibonacci numbers indeed satisfy this other recurrence. Okay, but notice that we have n minus 2 and n minus 4. So we have to generate, we can ignore essentially half the terms, but we have to recreate the base cases. Because in our original form, 0 and 1 are the base cases, but if we only consider, let's say, the odd terms, then the base cases will not be 0 and 1 anymore. So how do we generate the base cases? Just compute them manually, one by one. So if it is 0, 1, use the original recurrence, you'll get these terms. And depending on the parity of n, you either get these two or these two. Okay? And then, after doing that, n is essentially approximately halved. And we can repeat the same process, getting newer and newer recurrences until n becomes small enough such that it belongs to the base cases now. Okay? So how slow or how fast does this work? So what are the things that we did? We took this polynomial, which we can get in O of k time. We computed q of minus x, which is just switching signs, so that's O of k time as well. We multiplied two polynomials. We can do that naively with O of k squared time. And then we generated new base cases. Each term can be computed in O of k time. So this part runs in O of k squared time. So everything that we did to have the sequence runs in O of k squared. So we get k squared value, which is much faster than probably any matrixes multiplication technique that you will get. At least the most general form. If you are trying to multiply matrices without exploiting some of its properties, you'll probably not get any better than k squared value. Okay? Is that clear?
But you are multiplying here two polynomials. What if you use FFT or something?
So how do you do this part then? Can you do this faster? You can certainly do that with this one. You can compute this in case in K log K time using FFT or something. But can you compute the new base cases faster than K squared? I haven't discovered any technique yet. So if you can, that will be nice. Okay, if you can do this part in K log K time, then that's really nice. Okay? So
This only is very tight now. Like we are only coming from k to the power 2.36 k square.
remember that this is the state-of-the-art multiplication. This is the state-of-the-art matrix multiplication. You're probably not going to get this complexity. You'll probably get k cubed. Okay, this is very, very complicated. I don't think anyone has ever implemented this for a programming competition. Okay? This is just the theoretically best one we have so far in multiplying two matrices as fast as
So
possible.
it will be like
I've seen a problem in a code chef long challenge which did that.
Yeah.
And I read the editorial and went over it.
What? And
I read the editorial and I understood nothing.
okay. So what about what you were saying?
So it's not using any programming context.
I mean this one is not using any programming context. But the k cube, of course, is just matrix multiplications. And this one, that's easy, right? And we can easily kill k cube and only allow k squared. So this one is pretty much very useful. Okay? Any other questions? So actually, you mentioned a code chef long challenge.
That's
And
10.
what?
Coaching long challenge is 10.
Is 10 days, yes. So a very similar problem like this appeared in a code chef long contest. I made the editorial for that. That's why this is very similar to that. Okay? So, but luckily we tackled this because you mentioned you didn't understand the editorial. And that's pretty understandable. I think there's a lot of ideas in that editorial as well. Okay? Any other questions? So we will not tackle this today. But in fact, I will tell you as well that you can even do this in k log n time using another different technique. That includes FFT, among other things. Okay? If you want to know about it, try reading that editorial. The problem code is RNG. Okay?
Coachef.
In CodeChef. The editorial describes this solution. Okay? But as far as I know, it's only used for that particular problem. I haven't seen that technique used anywhere else. That's what, and this is the hard problem in that no contest, so you know that it's a very original idea. Okay? But for many purposes, this will help you improve your solution. For example, you can't improve your matrix anymore. You can just cheat and use the generating function. Okay? So one final note. We only solve linear recurrences that are of this form. But remember, we had mutual recurrences earlier, which we can easily solve with matrices, right? We just have to have the right column matrix and have to have the right matrix. How do you use this technique to solve those ones as well?
If we do something like, say, we have a composition of two linear recurrences, then we will take the common terms together and then use that formula to finally add them up.
Yes, but that only works if you can do it by hand. What if k is in the thousands? And the recurrence actually depends on the input. How do you automate that process of extracting the recurrence by hand?
Not possible.
What?
It is not possible.
It's not possible? Maybe? Okay. So the answer is actually it's possible. So that's why I was asking how do you do it. So I will not explain all the details. The idea is, let's say you have a matrix and you have two column vectors and we want, let's say, this term. So if you multiply this matrix repeatedly, you'll get some sequence on this row. And let's say we want to find a linear recurrence for that sequence. What we can easily do is generate, so let's say this is k by k, generate 2k plus 1 terms here, and then try to find the linear recurrences using Gaussian elimination. So, how does that work? Let's say I gave you some sequence, 0, 1, 1, 2, 3, 5, 8. You don't know what it is, right? You don't know what it is. But I tell you there's a clue that this one satisfies an order 2 recurrence. Okay? So you know that you have some form like this. So you know that 1 equals A, 2 equals A plus B, 3 equals 2A plus B. You have a system of recurrent equations. You just get enough. Just get enough of them and you can extract the coefficients. Okay, that's what you can do. Although that runs in k cube, you know. Okay? That's one thing you can do, especially if everything is fixed. You can pre-compute this, maybe it will help. Okay? This is k cube, but afterwards you only need k squared log n. So that's better than doing k cube log n multiple times. Okay? This one's clear. So if I tell you that some sequence has an order k recurrence, you can extract the coefficients using system of linear equation techniques. Okay? So the tricky part is you have to generate the recurrence first for 2k terms, or 2k plus 1, just so you can generate the equations here. Okay? Unfortunately, when doing that, this process takes k cube time and solving that takes k cube time. So at this point, I also would like to mention that it's also possible to do it in k squared time, at least that part. This one, not necessarily. Although this is fine in most cases, especially if this matrix is sparse. If this matrix is sparse, then multiplying it will be faster than k squared. Okay? So you can do this part faster than k cubed, and then use the k squared technique to extract the coefficients. Okay? I forgot the name of that algorithm, but there's an O of k squared algorithm to extract the coefficients of any linear recurrence.
Is it method of differences?
What?
Is it called method of differences?
No. So the name is actually names of some researchers. So I forgot someone's algorithm, something like that. Okay, but this part can be done in k squared, and then using the generating functions technique, we can do everything in k squared level. So do you have any questions? Is everything somewhat clear? Okay. So I think the new technique here is the generating functions technique, where you multiply by q of minus x. And then I also mentioned that it's also possible to do it in k log n time using a particular technique that works. Just read the editorial for RNG. Okay. And another side note, sometimes the matrix has a special form. Sometimes it's not any random matrix with random numbers everywhere. In certain cases, some matrices can be multiplied faster than k cube time if they have a certain form. So sometimes that's part of the problem as well. If you can spot that, you might want to exploit that as well. Yes?
I have a doubt in that. that, how come that complexity is O of k cube? Like when we have to generate k numbers, so that would be O of k square.
You have to generate k numbers, but multiplying this thing is k squared each. Right? But multiply it once, that's k squared. You have to do that 2k times.
If we use a simple dp, then that would be k square.
What do you mean simple dp?
Like if we store it in an array.
Which one? This one?
If we see it as a linear recurrence problem rather than a matrix problem, so then we can.
What I'm saying is that, let's say you have this weird weird system. Something like this. We can easily solve this with matrices. But do you immediately see the linear recurrence for f? That doesn't involve g at all? No, you have to manipulate this. Okay? And in fact, for larger systems where everything is interconnected to each other, that's going to be impossible to do by hand, or at least very, very hard. Okay, so the easiest way is to just multiply the matrix that you have to generate the sequence. Okay?
I think you can maintain two arrays and that will also.
What do you mean two arrays? Which ones do you want to maintain?
Like one array for f and one array for g.
Oh, this is because it's a small example. What if we have 100 recurrences that are interconnected to each other? Can you still do that? Will it still take k squared or k cubed?
I think it's straight.
Let's say okay, let's give a slightly larger example. Okay? So let's say something like this. And try thinking of an even larger system. Okay? Not just 3. Let's say k systems. Okay? And these are the things that you have. So you have a k by k matrix here. How do you think can you compute f of n here? You have to compute all of this, right? That's gonna take k squared each. Even if you do it by matrix form, if you do it manually, that's gonna take k cubed time, right? That's the point of this. So especially if the matrix is not sparse, if there are a lot of terms, non-zero terms here, then it's gonna be slow. That's why I'm making a point about this matrix being sparse. If this is sparse, then you can maybe exploit that. Okay, let's say there are only ones here and there, and then there are a few numbers here and there. It's going to be fast to multiply that, right? But if this is very dense, then you have basically no choice but multiply it every time, and it's going to be equivalent to the negative algorithm. Okay? Does that answer your question? Any more questions?
That RNG problem was asked in long challenge.
Yeah.
Yeah, so like what are the AC solutions during the contest like that? What are they k log n or something different?
I think most of the accepted solutions got this complex. Okay?
No, that is the algorithm you wrote in the editorial. That one or something different. Then we can also exploit that.
Can you repeat it?
Yeah, so that is you are specifying some algorithm to solve this problem in k log n. So did you go to the AC solution like where did that algorithm itself or something different?
Sorry. So I just mentioned everything I know. The solution I think of the author is k log n. My solution is k log n. The solution I explained in the editorial is k log n squared. So what?
Like how many algorithms are the algorithms different?
I'm not pretty sure. When I wrote the editorial for this, I didn't ask the author of this or her solution. I came up with my own, independent of the tester, etc. And I did that because that's what I'm more comfortable with to explain. I think sometimes it's hard for me to explain solutions made by other people, especially if they're too technical. Okay? You can probably read the setter code if you want to know. Try to read the setter code. Any more questions? If not, then I think that will be the end of my session for okay, thank you.